Hi, I'm Aiden Tarble, and I'm presenting Mechatronics Engineering Problem Solving in Python for EGR214 Numerical Methods for Engineers. First of all, why do we want to use Python? Well, solving things analytically causes a lot of problems with human error like rounding, logical fallacies, and miscalculations. And creating a program is especially useful for repeatable problems because you can just swap out the same, you can use the same program and just swap out the numbers every time. And that's useful for accuracy and for efficiency. And there can be incredibly long problems where using a computer would be much faster, which is another case of efficiency. So, problem one, this is about a DC motor, which is fundamental in mechatronics. We want the relationship between the input voltage, V for volts, and the resulting angular velocity of the motor shaft, which is given as omega in radians per second. And the step response for a specific motor is given by omega of t, so that is when 1 volt is applied. The system's instantaneous power dissipation in the armature winding can be given by P of t is I of t times V, so that's going to be the power in watts W, and the current is I in amps. So the two goals for this problem, plot the omega of t and P of t on the same graph with different y-axes, and find the max power dissipation. Now we have some givens here. Omega of t is this exponential function in radians per second. We have a time interval t, which is 0 to 1.5 seconds with a sampling period of 0.01 seconds, so we're taking a measurement every 0.01 seconds. And the time constant is 0.25 seconds. The current is a similar exponential function in amps. And we have a steady state gain. What that is how many radians per second it increases per volt applied. So K is 8.5 radians per second per volt. Then we have P of t as I of t times V. Now on the left, you'll see how we're going to graph these things by hand. Omega of t, we have to plug in K and the time constant, 8.5 and 0.25. P of t, we have to plug in the time constant and the volt, so that's 0.25 and 1. For finding the maximum power dissipation, we have to take the derivative. Once you do that, you'll see that it's always positive, which tells us that it's an always increasing function since the rate of change is positive. And the max of an increasing function is just the right bound. So we plug in the right bound 1.5 seconds for t, and we get about 0.798 watts. Now on the Python side, we'll import NumPy. And from NumPy, import asterisk basically just means it's going to import everything from NumPy, and you also don't have to write NumPy every time you want to call a function from it. That's what the asterisk does. And then we're importing the matplot library as plot just for convenience when writing it. So you'll have to type plot every time instead of matplot library every time. Now, to define our variables, we have t as an array, so we need to use the linspace function. That's going to go from 0 to 1.5 with 150 evenly spaced values in between. So that's going to give us our interval 0, 0.01, 0.82, and so on. Then we have the time constant as capital T, since you can't type Greek letters into Python, and that's 0.25, K is 8.5, and V is 1. Our functions, and similar to time constant, I had to do lowercase w as omega. But omega of t would give us this exponential function, I of t gives us this exponential function, and those are using exp for e to the power of something. Then we have p of t for the power function. And for graphing, this was a bit tricky. You notice there's a lot of stuff for graphing. We have to define the title at the top. Then we have to plot t versus omega of t, and we'll make that one red. Now, since the x-axis is going to be time, the limits for that are just the min and max of t. Then for the y bounds of the graph, what you'll see in the y dimension, just doing 0 to 10 just because it'll look pretty, it'll fit the graph nicely. Very convenient. Then we have to use the twin x function. What that will do is it'll create another y-axis that shares the same x-axis. So that's how we graph our t versus p of t, and I'll make that one blue to contrast the red. Now our x label is time, our y label is the step response in radians per second. Then we have another y label for the other axis, which is power dissipation in watts. Then we have some grid lines along the x-axis, so that's going to show some vertical grid lines. Then we have some labels for the functions, and I have some coordinates given here. Then, rather than having to take the derivative and do all that stuff for the max, NumPy has a max function, so we'll just do the max of p of t to find the maximum, and we'll print that and round it to 3 decimal places. And you can see all that here. The max power dissipation rounded to 3 decimal places, 0.798 watts, which is what we got before in our analytical solution. Then we have our two graphs with different y-axes and the same x-axis, and those vertical grid lines. So for this problem, in conclusion, the objective was to plot the angular velocity of the motor shaft and the power dissipation on the same graph with different y-axes. And I need the max power dissipation as well. The max power dissipation was solved analytically by taking the derivative of the function to see it was always increasing, leading us to the conclusion that we needed to plug in the right bound. This was done in Python by establishing values, defining functions, then by using the numpy max function for the power dissipation and the matplot library, notably the twinx function for graphing. For the second problem, it's about a motor again, and we're using a rotor encoder, which is just a measuring device, to measure an angular position of the motor shaft. The true angular position, what it should be, is modeled as theta of t in radians. However, when we measure it, there's a bit of a DC offset and a high frequency noise corrupting our measurements, throwing them off, and that'll be modeled as y of t. We try to reduce this with a software filter. We try to reduce the noise, and that will be given as y filtered at sample n, and that is the average of the current and previous n-1 samples, which I'll show you in a second. So the two goals for this problem: plot the true position, what it should be, the noisy signal that is messing up our measurement, and the filtered signal, what we try to do to filter out the noise. And also calculate the RMSE, which is the root mean squared error between the filtered signal and the true position. So we want to see how effective was our filter. So our theta of t is given at the top. That's just a linear function, 2 pi t. We have our y of t, which is that theta of t with a bit of offset there. That's the 0.1 sine of 30t plus 0.05. We have our time interval, similar to the last one, but it's 0 to 3 seconds. And we're given a sampling period that's 0.01 seconds. So we've taken a measurement every 0.01 seconds. Now y filtered at sampled n is this series here, and it calls upon the y function. It calls for the n-ith element. Notice those are brackets, not parentheses, so that's not y of n-i, that's the n-ith element of y. And then the root mean squared error, similar to that, calls upon the y filtered function and the theta function at sample I, and it has a series as well. Then we have the moving average filter, m equals 10. That's just a value we'll plug into the filtered signal. Now for the y of t, I've just shown that you can plug in theta of t, which is 2 pi t, into the y of t function. Now for doing this analytically, it's practically impossible unless you want to sit here for 2 hours and write out all these series. For the y filtered series, it's like 10 terms you'd have to add together, which no one wants to do that. But for the root mean squared error, that's about 300 different terms, and no one wants to sit there and subtract and locate elements and square and divide by n and square root 300 different things. So if you were to plug that into your calculator, you get 0.24, but no reasonable person would actually do that, and that's why we have Python to help us out here. So on the Python side, we've imported numpy as np this time. Instead of using the asterisk, I've used import as np. So just to show another way of doing it, so every time I call from a numpy function, you'll see an np there. Similar to last time, I imported the matplot library as plot. So every time you see a matplot library function, you'll see a plot there. Then I've imported pi. So to define our variables, once again, we'll put 0.01 as our sampling period, and t is still an array, except instead of using linspace, I've used a range. Because while linspace defines your array by the amount of samples, this one defines it by the period between the samples, which we were given, so I felt it relevant to incorporate it into our array here. Then we have m equals 10, and n is going to be the length of t, so that's going to account for all the samples. The length of t is going to be 300, so that's just the amount of samples in our array. Now for the functions, we've defined theta of t as 2 pi t, and y of t with the little bit of noise added onto the theta of t function. The y filtered was a bit trickier because it was a series, but that's what for loops are for, so we'll initialize it as 0. Then for I in range m, notice that's not m-1 because Python's going to read that as I equals 0 to the range value -1, which is what the series says, I equals 0 to m-1. Then we will add to itself the y at sample n-i. Then we'll divide by n. And now for plotting purposes, and also for the brackets, the element calling, part of the functions, we'll have to define the functions as arrays, because you can't call an element from a function that has not yet been defined. You have to call it from an array. An array is a list of numbers. So you can only call an element from a list of numbers. That's why we have to define our functions as values first. So we define theta of t as theta values. Similarly, we've defined y of t as y values. For y filtered values, we did it a little bit differently. So I've initialized it as an n amount of zeros, so that's 300 zeros. Now for sample n, in range capital N, so that's going to be the sample n at all 300 samples. It will do this if-else argument here. And the reason we've done this is because, notice it's the n minus ith sample of y. So if that value is negative, it's going to return an error because you can't have the negative sample of something. You can't have the negative second sample, can't have the negative third sample. That's not a thing. You can only have the first, second, third sample, and so on. So if n is bigger than I, that works fine, but if n is less than I, that's going to return an error. That's why I have if n is greater than or equal to n minus 1, which is the biggest I value. It's going to work like normal, but if anything else, it's just going to return a 0 to avoid an error. And similar to the other one, the y filtered, this one's a series, so I have to use a for loop. So for I in range n, it's going to add to itself, and then square root and divide by n. Then we'll print that root mean squared error and round it to do decimal places. For plotting, I'm plotting t versus the y values, t versus the y filtered values, and t versus the theta values, and labeling them all. Then I created a legend. Then I labeled the x-axis as time, the y label as the angle in radians, and the title, and then we're showing the plot. That'll give us this. We have these three curves here. The green one is a bit hard to see, but it's a straight line. That's the true angular position, what we wanted. The blue one is the noisy one that happened when we were measuring it. And the orange one is us trying to filter out that noise and get closer to the green line. And you'll notice the error between the green line and the orange curve is 0.24, so that's a pretty low error, so that means we've done a pretty good job at filtering out this noise. And the reason there's that notch at the bottom is for those values of n that were less than n minus 1 that returned an error that I replaced with 0. So you notice it's 0 for a little bit of time, then the curve works like normal. So in conclusion for this one, the objective was to plot the true, noisy, and filtered angular positions on the same graph, and I need the root mean squared error between the true and filtered positions. The error was solved analytically by evaluating the series step by step to figure out what the value would be, and this was done in Python by establishing values, defining functions, and by using the for loops for the series, and brackets to locate specific values from arrays. Then I used matplot to graph the functions.